Physics 2212, Lab 4. My name is Max Minsky. So the purpose of this lab is basically to predict the behavior of circuits with resistors in series and parallel, and to simulate the behavior of resistors and capacitors using the FRIT simulation. So we're also going to be using multimeters within the simulation to measure current and electric potential, and results being that the current in the dual resistor circuit was 0.02 amps, time constant was 5.984 seconds, and the current and potential difference calculated and experimental values agree. And the higher the resistance, the longer it takes a capacitor to charge. All kind of intuitive. So key concepts, we've got the node rule and the loop rule. The node rule being that the current entering a junction has to be the sum of the currents at the junction, which is basically just the conservation of charge. And the second one is basically just the conservation of energy, right? The change in voltage for the round trip has to be zero. So the electrical resistance is just calculated using Ohm's law. So it's, voltage over current. And when in parallel, the equivalent resistance is pictured below, the sum of 1 over the resistance of each resistor. Um, when in series, however, the equivalent resistance is just the sum of the resistance of the resistors. So capacitance, this is a measure of how much charge can be stored in the capacitor per unit of potential difference. It's also equal to epsilon naught times A over S. So for you. So with the model, that the system is basically the ammeter or the voltmeter. It's, I guess, both in this case. And the surroundings, it's like the circuit itself, as pictured below. So first part constructed a circuit with two 1.5 volt batteries, so 3 volts total, two resistors, which are 47 and 100 ohms, and two ammeters. So the predicted current was 0.0204 amps, where the actual current was 0.02 amps, and the reversed ammeter would just be the negative. As intuitive. And you can see some calculations down there that corroborate this. So part two, same as part one, but the second ammeter is replaced with a voltmeter. So the predicted value is voltage is 3 volts and the current is 0 amps, which is also intuitive because 3 volts from the batteries and there's a break, so there would not be any current flowing. And this is what we got in experimental values. So third part, basically, we close the circuit for part two, and we measure the potential difference between points. You can see them listed below. And these all support the loop rule because the sum of all these turns out to be zero. As you can see, negative 2.04 minus 0.96 plus 3 volts, that's zero. Now, part four, we basically reconstruct the circuit so that the ammeters are in parallel with the 100 ohm resistor. And the current measured by ammeter increases from 0.02 to zero point zero 0.06 amps. This is because the current split, and some of the current encounters resistance, some of it doesn't, and overall the current increases once it regroups. You can see some maths down there in the bottom right, basically showing proving this, corroborating my claims. So part five, what happened was basically calculate the resistance of the resistors, ammeter, and the wire based on the experimental values. So the resistance is just calculated with Ohm's law, which we get 48 ohms. We get the resistance of the 100 ohm resistor is 102 ohms. Resistance of the ammeter was 0 ohms, which is experimental. It's just obviously reality it would have some sort of resistance. And the resistance of the wire, same idea, 0 ohms. Now part six, we constructed a resistor capacitor circuit with 100 ohm resistor, with 10 ohm resistor, uh, 200 milliflorin capacitor, and a 9 volt battery. So the measured time to charge this was actually well, you can see the current was zero both times. And we repeated this with the 20 ohm resistor. Results, we get the charging time is actually 15.4 seconds, and the discharging time is 50.2 seconds for the 10 ohm. And the 20 ohm resistor, charging time is 25.9, and discharging time was 27.5 seconds. Now, part seven, basically construct RC circuit with a 9 volt battery, 30 ohm resistor, and 2 form capacitor. So, charge capacitor, record potential difference, move battery, pause circuit in the FET simulation. Then, for each second, record the potential difference across the capacitor, and record the potential difference for 20 seconds. Then, plot ln of V over V0 against time, where V is at time t and V naught is initial. Using the equation over there, slope is -1 over RC, and then we solve for RC, which is the time constant. So some model shortcomings is that we calculated resistance values that are greater than actual resistance of the resistors. In the FET simulation, this is due to the ammeter's precision, which is only to the hundredth place. So that's sort of a shortcoming. And it's also another error source, lack of the ammeter precision. There's also the fact that we were, routing during the calculations and the timing error when discharging, terminating charge and discharge times. So, what if we were to do this lab in real life and use an actual ammeter instead of an ideal simulated ammeter? What's the difference about a real ammeter and how would it have affected the circuits you hooked it up to? Well, the real ammeter has non-zero resistance, right? So the current would be decreased slightly. Um, and yeah, I mean, it would not be the same value then because there's a greater resistance, slower current, wrong values then. So that's one source of discrepancy. Now, what if we were actually doing this lab in real life and used real battery, charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? Explain. So basically, the ideal model predicts that a capacitor charges instantaneously, which obviously would not happen in real life, right? It takes time to charge a capacitor. This is because the wires also have a non-zero resistance, which would also increase the amount of time for the capacitor to reach fully charged state. And furthermore, the capacitor has resistance, so several sources of error. Anyway.